Equilibrium and Le Chatelier's principle. So when you have a reaction that is at equilibrium, that reaction will remain at equilibrium unless a change is performed. And by a change, I mean like changing the temperature, changing concentration, or changing pressure. We use Le Chatelier's principle to predict what, like, how these changes are going to affect the equilibrium. If you change the concentration, what's going to happen to your equilibrium system? So for example, if you have a reaction at equilibrium and you add more of the reactant, what's going to happen with that amount that you're adding? How is that amount that you're adding affecting your equilibrium constant for that reaction? So all of those things are explained using Le Chatelier. So I'm going to try to do a very simple example here so you can see how the equilibrium is affected by changes and how we apply Le Chatelier's principle to predict how those changes are affecting the equilibrium. So I'm going to put here R for reactant, P for product. The equilibrium constant will be your concentration for product over the reactant. So let's assume that that equilibrium constant is equal to 2. No units because this is concentration over concentration. So the equilibrium constant value has no units. All of the units will cancel out. So I have my numerical value for K right there. It's just 2. And I'm just giving you a number. Now let's say that I'm going to add more reactant to my reaction flask. So you have a flask containing all of this, the reactant and the product that it's being formed, all of them, like the concentrations are at equilibrium. Okay? So I'm going to add more reactant. So you see, if you're adding more reactant, the concentration of your reactant is increasing. So how is that going to affect your equilibrium constant? It's a constant. Okay? So if you add or increase the concentration of your reactant, this number right here is going to be increasing, which means that the value of your equilibrium constant will go down. Okay? So that's what's going to happen if you add more reactant and nothing else is happening in your reaction. Now, what Le Chatelier's principle is telling you, okay, so if your system is at equilibrium and you add something, this is my example, I'm adding something, your actual reaction is going to find a way to minimize that change. Okay, the change is increasing concentration of my reactant, so the reaction is going to find a way to minimize that change. Minimizing that change, what that means is that that amount of reactant that I'm adding to my reaction flask, it's actually going to be used up. You see, if that amount of reactant is being used up, what's happening is that you're forming more product. So if you're forming more product, how is that going to affect your equilibrium constant? Again, the concentration of your reactant now will be decreasing because it's being used up, while the concentration of the product it's going to be increasing. So the reactant that is being added to that reaction, it's actually being used up, forming more of the product. So now that consumption of that reactant that I added, it's going to happen until your reaction reaches equilibrium again. And you get the same numerical value for the equilibrium constant. It's a constant, okay? Now, another way of looking at this, if you're adding, right, that's what I'm doing. I have my flask with my reaction at equilibrium and I'm adding more reactant. So you have more particles of the reactants. They will find each other easier. They will collide and they will form more product. This is something else that is happening. It's the same thing but explained in another way. So whatever changes you're doing, your chemical reaction is going to find a way to minimize those changes. And we can actually predict how the reaction is going to minimize those changes using Le Chatelier. So we're going to be looking at three different types of changes. So the first one is the easiest one, which is just changes in concentration, adding more reactant, adding more product, removing the product. So you can think about Le Chatelier's principle as a prediction of how to get more product out of a reaction. Remember, like the equilibrium is going to determine how much product you're getting. If the reaction gets at equilibrium and you have a lot of reactants present, it means that when the reaction reaches equilibrium, you have a small amount of product, which is what you're trying to get. So we can actually do things to form more of that product that we want. So one of those things that we can actually do is changing concentrations, increasing or decreasing concentrations of products or reactants. Increasing concentration, increasing concentration of reactant or product, not just for one of them. This applies for anything. Increasing concentration means that the equilibrium will be shifted or moved towards the direction that uses up that amount that you're adding. For example, if you're increasing concentration of a reactant, your reaction is going to find a way of using up that amount. Using up the amount of a reactant means that the reactant will be used up to form a product. So whenever you're increasing the concentration of a reactant, what is happening is that the equilibrium will be shifted towards the product, forming more products. If you're increasing the concentration of a product now, you're adding more of that product that is being formed in the reaction. Now you have an equilibrium, right? It's moving both ways. That amount of product that is being added will be used up to form more of the reactant. So the equilibrium will be shifted towards the reactant side. Decreasing concentration now. If you're decreasing the concentration of a reactant, right? Now your equilibrium system, your reaction is going to find a way of making up more of that reactant that we're taking out. If you're decreasing concentration of a product, your reaction is going to find a way of making up more of that product that we're taking out. So whenever you're adding a substance, okay, the equilibrium will be shifted in the opposite direction. Okay? When the equilibrium is shifted in the opposite direction, what is happening is that you're using up that added substance to form something else. Okay? Whenever you're removing a substance from an equilibrium system, your reaction is going to find a way of making more of that substance that you're taking away. So the equilibrium will be shifted in the same direction that you're taking away that substance, because your reaction is finding a way of making more of that substance. So I have an example here. It's a generic example. And I have all of that in a box because when you're looking at a reaction at equilibrium, the reaction is in a flask. All of it is on the same container. It's not like you have A plus B on one side and AB on the other side. All of this is happening in the same place. Everything is together. So I have a list of changes and we're going to predict what's going to happen to the equilibrium. So I'm going to do 3 of them and then you can do the other 3. So I'm going to start looking at A. A is a reactant, right? Now the change is adding more of A, which means that we're increasing concentration of A. If you check, adding or increasing shifts the equilibrium in the opposite direction. If we're adding more reactant A, your reaction is going to find a way of going back to the original equilibrium. So for your reaction to go back to that original equilibrium, now that you have more of that reactant, it will have to use up that amount that it's being added. So adding a reactant will always shift the equilibrium in the opposite direction, which is towards the right side. It shifted towards the right side. Your products, because that amount of A that it's been added, it has to be used up, and it's used up forming more of what you have on the product side. Adding AB, that's increasing again. Okay? Now AB, it's a product, you can see it, it's on the product side. If you're increasing the concentration of AB, your product, your reaction will regain equilibrium, the original equilibrium again, when that amount of product is being used up. For your reaction to use up that amount of AB, it has to be by forming more of what you have on the opposite side, which is A and B. So adding AB, which is on the product side, will shift the equilibrium in the opposite direction, forming more of AB. You see, when you're adding something on the reactant side, the equilibrium will be shifted towards the product to use up that reactant that you're adding. When you're adding something on the product side, the equilibrium will be shifted towards the reactants to use up that amount of product that it's being added. So I'm doing one more. Let's do removing B. Removing B means decreasing concentration of B. Decreasing concentration of B, which is that reactant right there. And I'm going to put my arrow pointing out because B is being taken away from your reaction. So when you're removing B, the equilibrium will be shifted in the same direction because you have to make up more B to regain equilibrium again. So whenever a concentration is being decreased or you're removing something from your reaction will always shift in the same direction of that substance that is being removed. Your reactant B is on the reactant side. Since you're taking away something from the reactant side, the equilibrium has to be shifted towards the reactant side to make more of B. If you're taking away something from the product side, removing a product will shift the equilibrium towards the product again to make up more of that product that is being removed from the reaction flask. The second type of change is changes in temperature. So before we get into all related to everything related to equilibrium, let's review the type of reactions that we can have. We can have endothermic reactions and exothermic reactions, depending on the value for the change in enthalpy. If you have an endothermic reaction, it's because your reaction is absorbing heat. If the reaction is absorbing heat, the change in enthalpy will be positive and you have an endothermic reaction. If a reaction is releasing heat, the reaction releasing heat means that you will have a negative sign for the change in enthalpy. And that's why the reaction is exothermic. It's releasing heat. Delta H is a negative value. We can look at heat as an amount, okay? It is an amount that is needed for a reaction to happen. It is an amount that is given off if your reaction is exothermic. So depending on which type of reaction we can have heat as a reactant or as a product. If your reaction is endothermic, it means that for that reaction to happen, the reaction needs to absorb heat. So the heat will be a reactant. Without that amount of heat, that reaction is not going to happen. If you have an exothermic reaction, your reaction is releasing heat. So the amount of heat is a product because the reaction is actually giving off that amount of heat. So with an exothermic reaction, the amount of heat is a product of the reaction. With an endothermic reaction, the amount of heat is a reactant for that reaction. So you can see that's why I have what I have right here. For exothermic reactions, the first one, the amount of heat it's a product. For endothermic reactions, the amount of heat it's a reactant. Exothermic reactions are giving off heat. Endothermic reactions are actually using heat. Now, when we're looking at changes in temperature, what I mean is increasing or decreasing temperature. Those are the two changes. Since we're looking at heat as an amount, the same things that we did with concentrations are going to be applied in here. If you're increasing the temperature, increasing temperature means that you're adding heat. Adding a substance or adding heat, it's going to shift the equilibrium in the opposite direction, right? So that reaction will be using up that amount that it's being added. If you're decreasing temperature is the same as removing heat. So in the same way that we're removing a substance from a reaction, and your reaction is going to make up more of that substance that is being removed, the same thing applies to temperature. If you're removing heat, the equilibrium will be shifted in the direction that will make up more heat to replace that amount that is being removed. So when we look at my first reaction here, the exothermic one. So I'm looking at A plus B going to AB, exothermic. So the heat it's on my product side because it's an exothermic reaction. Looking at my table down here, I'm going to look at adding heat first. I'm adding heat, and this is for my exothermic first. Adding heat to an exothermic reaction. The amount of heat is a product always for exothermic. So when you're adding heat, you're increasing heat on the product side. So increasing or adding will shift the equilibrium in the opposite direction, right? To use up that amount of heat that is being added. So for that amount of heat to be that it's being added to be used up, the equilibrium will be shifted towards the reactant side. You're adding something that you have on the product side. So your reaction is going to find a way to use up that amount that is being added. To use up that amount that is being added on the product side, the reaction needs to form more of the reactants, using up that amount that is being added to form more reactants. If we're adding heat, and now I'm going to be looking at the endothermic. For your endothermic reaction, the heat, it's a reactant, right? It's endothermic, and that reaction is not going to happen unless it absorbs heat. So it's a reactant. So if your heat is a reactant and now we're adding more heat, we're adding more of something that you have on the reactant side, the reaction is going to find a way of using up that amount of heat that we're adding. To use up that amount of heat that is being added, it needs to form more product. It will be consumed by forming more of the products. So whenever you're adding something means that the equilibrium will be shifted in the opposite direction to use up that substance that is being added. If you're adding more heat to an endothermic reaction, the heat is a reactant, so the equilibrium will be shifted towards the product to use up that amount of heat. Now let's look at removing heat. Exothermic first. The heat for an exothermic is a product. Whenever we're removing something, and this applies for concentrations too, removing something means that the equilibrium will be shifted in the same direction of whatever substance you're taking away. If we're taking away heat from an exothermic reaction, we're taking away heat from the product side. So the equilibrium will be shifted towards the product to make up more of that heat that we're taking away. Looking at the second one again, endothermic. Removing heat from an endothermic reaction. Endothermic, you have the heat as a reactant. Whenever you're removing something, the equilibrium will be shifted in the same direction of whatever substance we're taking away. So if you're taking away heat from an endothermic reaction, it means that you're taking away heat from the reactant side, and the equilibrium will be shifted towards the reactants to make up more of that heat that we're taking away. So now you have an example right here. You see, I'm giving you a reaction and a delta H. So when you have your delta H, the sign is telling you if that reaction is endo or exothermic. This one with the positive delta H, you have an endothermic reaction. So now based on that information, you can place your heat. Okay? You're going to place your heat on the reactant or on the product side depending on the delta H value. So now prepare your table in a similar way to what I have right here and predict what's going to happen to your reaction, right? And this is just for endo because it's a positive. So you need adding heat and removing heat. So what's going to happen to your equilibrium if you're adding heat to your endothermic reaction here, or if you're removing heat to your endothermic reaction? So you can predict just by writing the arrow pointing to the right or pointing to the left. Pointing towards the right means that the equilibrium will be shifted towards the product. Pointing towards the left means that the equilibrium will be shifted towards the reactant. The third change that we can have for a system at equilibrium is changes in pressure. So before we look at the changes in pressure, let's review the relationship between pressure and volume. Pressure is a force, and it's a force because the particles in the container are going to be colliding with the walls of the container as they move around. So those collisions are going to generate that force. So when you're looking at the boxes that I have here, you have the same type of particle, the dots are the same color, and you have the same amount in both boxes. So I have 6 dots in each one, they're the same color, so we can assume that you have the same type of substance and the same amount. Now, those particles are moving around, and when they move around, they're going to be colliding. And those collisions are going to generate a pressure. So now the question is, in which box you're going to have a higher pressure, the one that you have on the left or the one that you have on the right? So the pressure will be higher on the box that you have on the left. The reason is that you have a smaller box, so the number of collisions that you will have with the walls of that container is going to be higher. You have a smaller space, your particles are moving around all the time, and you will have more collisions. So the pressure will be higher in this box. In this one, your particles are still moving around, they're still colliding, right? But since the box is bigger, right, the number of collisions will be smaller. There's less chance of your particles moving around and hitting a wall on the right side because you have a larger box. So you have a smaller pressure for that one, which means that you have a higher pressure. And assuming that that's not just a two-dimensional box but a three-dimensional box where you have an actual volume, the higher pressure will happen when the volume is smaller. The smaller pressure with a larger volume. So that's the relationship between pressure and volume. The greater the volume, the smaller the pressure. So when we have a reaction at equilibrium, changes in pressure are going to affect the equilibrium in a similar way to when you have a reaction at equilibrium and you change concentrations or you change the temperature. Increasing the pressure is the same as decreasing the volume. They are the same. If you're decreasing the volume, the pressure will be increasing. If you're increasing the pressure, it's because the volume is decreasing. Another thing about pressure, besides the relationship that you have with volume, is the relationship that you have with the amount of a substance. You see, in my two boxes, I have the same amount, but if you increase the amount of a substance, the pressure will also increase. Pressure and amount, they are directly proportional. If you have more of a substance, if I increase the number of dots in my box, now the number of collisions will be higher, which is going to result in a higher pressure. If I remove some of the dots in my boxes, less dots means that you have a lower number of collisions, decreasing the pressure. And that's important when we're trying to predict what's going to happen to the equilibrium when changes in pressure are performed. So for example, increasing the pressure. If you're increasing the pressure by decreasing a volume of your container, the equilibrium will shift in the direction that decreases the number of moles of gas. If the equilibrium is shifted in the direction that decreases the number of moles of gas, now you will have a lower number of collisions and the pressure will go down. Remember, your reaction is trying to find a way of going back to the original equilibrium constant. If you're increasing the pressure, right, your number of collision is higher now. If your reaction now forms a lower number of moles of gas, now the number of collisions will go down and the pressure will go down again. So we're looking at changes in pressure for equilibrium systems containing gases. Now let's look at what's going to happen when the pressure is decreasing. Decreasing pressure is the same as increasing volume. Decreasing pressure will shift the equilibrium in the direction that increases the number of moles of gas. If the equilibrium is shifted towards the direction where you have more moles of gas, more moles of gas means that you will have more collisions and the pressure will increase back again. So let me do this example here. I have my reaction, 1 mole of A, everything is a gas. Okay? 2 moles of B, and what is being formed is 1 mole of AB2. So I'm looking at two changes here. Increasing the pressure of my container. Remember, all of this is in the same container. So increasing the pressure right there in red, increasing the pressure would shift the equilibrium that decreases the number of moles of gas. So I'm going to mark my number of moles of gas on the reactant side. I have 2 for B, 1 for A. That's a total of 3 moles. On the product side, I have a total of 1 mole of gas. So if the pressure is being increased, that's the change or the disturbance that it's happening to that equilibrium system. Increasing the pressure means that the equilibrium will be shifted in the direction that decreases the number of moles of gas. So the number of moles of gas on the product side, it's 1. So in this specific example, the equilibrium will be shifted towards the right side, which is where you have a smaller number of moles of gas. In that way, since now the equilibrium is shifted towards 1 mole of gas, the number of collisions will decrease and the pressure will also decrease. Increasing the volume. Increasing the volume, you see, you don't have that listed here. You have increasing pressure, decreasing pressure, but increasing volume is the same as decreasing the pressure. So decreasing the pressure will shift the equilibrium in the direction that increases the number of moles of gas. So looking at your reaction, on the reactant side, you have a total of 3 moles. If the equilibrium is shifted towards your reactants, now you're forming more number of moles of gas because you have 3 on the reactant side versus 1 on the product side. Increasing the number of moles of gas will increase the number of collisions, which will make that pressure go up again. Now you have a problem where you're going to apply everything, changes in concentration, changes in temperature, and changes in pressure.